Hi, my name is Jonathan Mousley. I'm a PhD student in mathematics at Duke University, and today I'm going to be talking about QR decomposition. I'm going to be making the assumption that people who are viewing this video are familiar with Gram-Schmidt orthogonalization, so if you aren't familiar with that concept, I'd recommend going to another resource and learning that first before jumping in and reviewing this video. Let's start by defining what a QR decomposition is. I'm going to let A be a matrix m by n with full column rank. And then I'm going to say that a QR decomposition of a matrix A is a matrix decomposition where Q has orthogonal columns with unit length and R is an upper triangular matrix with positive diagonal. Now to find a QR decomposition for A, we're going to use the Gram-Schmidt orthogonalization process. And remember, Gram-Schmidt is going to take in a basis for a vector subspace, V1 through Vn, and it's going to spit out a basis for that same space that is orthogonal. So I'll call that orthogonal basis that Gram-Schmidt spits out U1 through Un. So this is a basis for a subspace, V. And this is a basis for that same space V, and it's orthogonal. Gram-Schmidt provides the following formula. U1 is equal to V1, and then UK is equal to VK minus the following sum, where each element of this sum is a projection of VK, the kth vector put into the Gram-Schmidt orthogonalization process, projected onto the previous UJs. So essentially this UK is taking the original kth vector and subtracting all of the trouble that would cause VK not to be orthogonal to the previously selected U's. Now remember, we're hunting for a QR decomposition for the matrix A, which has full column rank. So how does Gram-Schmidt tie into all of this? Well, if A is a matrix with full column rank, then its columns make up a basis for the column space of A. So we can apply Gram-Schmidt to the columns of A to get out a set of vectors that is also a basis for the column space of A, but is orthogonal. Now the question is, how can we use this to actually get out a matrix decomposition for A? Well, we are going to use the formula that Gram-Schmidt provides us, and we're going to encode that formula in form of a matrix multiplication. I'm going to begin by writing A as a product B times C, where B and C are going to be related to my final matrices Q and R, but there's going to be a few modifications we'll have to make to them. Let me call the columns of A V1 through Vn, and I'm going to choose the columns of B to be U1 through Un. That is the vectors that Gram-Schmidt spits out when I put in the columns of A into the algorithm. Because I've chosen the columns of B, the entries of the matrix C are actually forced, and we can recover them by thinking about what it means for B times C to output V1 in the first column. The entries of C that have to do with the first column of the output will actually be the first column of the matrix C. And that first column is going to tell us what linear combinations of the columns of B I need to take to get out that first column of the matrix A. So because our Gram-Schmidt formula tells us that U1 is just equal to V1, those entries will be 1, 0, 0, 0, and so on. Now to determine the next entries for the matrix C, I'm going to write out our second Gram-Schmidt equation for k equals 2. I'm also going to go ahead and rewrite this equation isolating the variable v2, because this will actually allow us to read off what coefficients we ought to put into the matrix C. Similar to before, the second column of the matrix C tells us what linear combination we need to take of the columns of the matrix B to get out the vector v2. Now I can use that second way I've written my Gram-Schmidt formula to recover those coefficients exactly. Now reading from top to bottom for the second column of the matrix C, the entries are u1.v2 divided by u1.u1, 1, and the remaining entries are 0. Moving right along, I'm going to write out our Gram-Schmidt formula when k equals 3. And then as before, I'm also going to write this formula, but solving for the variable v3. Just like in the case of the previous two columns, the third column of the matrix C tells us what linear combination of the columns of the matrix B gives us the third column of the matrix A. The second way I've written the Gram-Schmidt formula above now comes in handy again, and I can read off the coefficients that ought to go in the third column of the matrix C. Going from top to bottom, they are u1.v3 divided by u1.u1, u2.v3 divided by u2.u2, 1, and the remaining entries are 0. Hopefully it's now clear how we can get the remaining entries for the matrix C. I can write out the Gram-Schmidt formula for the k case, and then just as before, I'm going to solve for the variable vk. Just like in the previous cases, I can read off the coefficients that ought to go in the kth column of the matrix C from the second way of writing the Gram-Schmidt formula. The good news is we're almost done. So far, what we've found is a matrix decomposition for the matrix A, B times C, where B has orthogonal columns, and C is an upper triangular matrix with positive diagonal. What we're in search of is a matrix decomposition Q times R, where Q has orthogonal columns that are unit length, and R is an upper triangular matrix with positive diagonal. So we're not quite finished yet because the matrix B does not necessarily have unit length columns. To address this, we'll modify the columns of B to have unit length. So here's our matrix decomposition, A equals B times C. So we're going to update the columns of B to all be divided by their respective magnitudes. And I'm now going to call this new matrix Q. But what I want to point out is the equality here is now broken because I've changed the matrix B, but I haven't done anything to the matrix C. We can fix this by modifying the entries of the matrix C as follows. Notice that the entries in the first row of C are always going to be multiplied by entries in the first column of the new matrix Q. So to account for the fact that I've taken this column U1 and divided it by its magnitude, I need to multiply the first row of the matrix C by that same magnitude of U1. I'll then repeat this pattern on all of the other remaining rows of the matrix C, and I'll call the resulting matrix R. This now is a valid QR decomposition for the matrix A, because all of the modifications we made in the first matrix have been canceled out by modifications made to the second matrix. I'd now like to close the video with a brief example of finding a QR decomposition for a 3x3 matrix. Let's begin by finding a matrix decomposition B times C for this matrix A, where again B is a matrix with orthogonal columns and C is a matrix which is upper triangular with positive diagonal. As it has been throughout this whole video, B will be a matrix whose columns are those outputted by Gram-Schmidt when we input the columns of A. Because U1 is equal to V1 for Gram-Schmidt, the first column of B will just be the first column of A, 1, negative 1, 0. And the first column of C will be 1, 0, 0, corresponding to the fact that the first column of A is 1 of the first column of B plus 0 of the second column of B plus 0 of the third column of B. We can then find the second column of B by using the Gram-Schmidt formula to find U2. So I can more easily find the coefficients that should be in the second column of the matrix C. I'm going to first solve for the coefficient u1.v2 divided by u1.u1. This equation tells me that the second column of the matrix A is minus 1/2 of the first column of the matrix B plus 1 of the second column of the matrix B. So in other words, the second column of the matrix C should be minus 1/2, 1, 0. Now I can use this formula to find the second column of the matrix B by plugging in the second column of the matrix A in for V2 and the first column of the matrix B in for U1. After some simplification, I discovered that the vector U2 is 3/2, 3/2, 0. That is, that the second column of the matrix B is 3/2, 3/2, 0. Now, to find the final columns for the matrices B and C, I will use Gram-Schmidt again, with k equal to 3. Again, I'm taking special care to first solve for the coefficients that go in front of U1 and U2, so I can more easily fill in the entries of the matrix C. Similar to before, using this equation I can now fill in the entries for the third column of the matrix C as being -1/2, -1/3, and 1. I can now find the final column of B by inputting the third column of A in for V3, the first column of B in for U1, and the second column of B in for U2, and simplifying. The result is the vector 0, 0, 1, which I can then input in as the final column of the matrix B. In our final step, we're going to modify this decomposition so that the first matrix in the decomposition is actually an orthogonal matrix. So we're going to divide the columns of the matrix B by their magnitudes, and then multiply the rows of the matrix C that correspond to those columns by those same magnitudes. The magnitudes of the columns of B are respectively √2, 3/2 √2, and 1. To arrive at our final result, we need to divide the columns of B by these magnitudes and then multiply the rows of C by these magnitudes. Explicitly, the jth column of the matrix B should be divided by the magnitude of Uj, and the jth row of the matrix C should be multiplied by the magnitude of Uj. This process then yields a valid QR decomposition for the matrix A.